Hey, hello, and welcome to the System Design for Parallel Programming. So, in this sessions, we are going to deep dive into the GPU architecture. So, earlier session, we have just get on with the CPU architecture, and it was a very quite informative overview. Now, we need to see that what is a GPU architecture, where we are going to write our parallel programming, which is one of the target. So CPU architecture was for task parallelism, whereas the GPU architecture is suitable for a data parallelism. Now, why this is a data parallelism is working great with the GPU? For that, we need to actually see and look and evaluate the GPU architecture. Now, in typically, these GPU architectures are designed with the hundreds and thousands of core. So if you take a look at most recent devices, you will find out that number of cores per GPUs are much higher than what it exists in the CPU. So the scale is like a 10 and 100 times higher. So that's what we are trying to look over. And what happens with the GPU, it gives us a high throughput. Means once you loaded the data, all the data has been processed and you are getting your result back, but it is not a low latency. Why? Because it takes a time. It's not in the latency, where in the CPU we can expect the latency in a range of a nanosecond, microsecond. Here we would be expecting the higher latency. That's what the GPU architecture is, and why this kind of issues we see, or why we observe this low latency, and why it is only suitable to the problem statement like a data parallelism, or why it is better for the machine learning application and inferencing. So for that, let's look at what is our GPU architecture. So the GPU architecture is typically connected with the PCI bus. So in this PCI bus, you can say that in every vendor, you can see the terms may differ, but what you can see is there would be a scheduler. So scheduler plays a very important role. So any task which we want to offload to work for the GPU has to be added to the scheduler first. Then this scheduler will decide that which GPU core will take that task and execute and collect the information and get back to our result where the user wants to get the output. So now to transfer the data, how we would be transferring the data. So once you have given the instruction to the scheduler that we need to transfer data from somewhere in the host location to the somewhere into the GPU. So there is a controller inside the GPU, which is this DMA, which is called as a direct memory access engine. So CPU, without having to intervene with the memory of the host and with the memory of the GPU, it can actually communicate. So there is a link which is established between the DRAM and the GPU memory directly, which is this global shared memory. So we can expect that the data coming through the global shared memory. So now our data will be in this global shared memory. Now what happens that any data which needs to be loaded into the core, it runs through this L2 cache. This L2 cache is common for a particular GPU die. So you can assume that it's like a one block which is having a multiple GPU cores, and this L2 cache. So after that L2 cache, so there would be a multiple cores of the GPU. So you can call it as a streaming multiprocessor. So you can see this wording, streaming multiprocessor. Or if you are into the terminology with the different vendors, then you can see the Nvidia, they would be calling it as CUDA cores. They call it as CUDA cores. If you are using an Intel GPU, they would be calling it as XC core. But this is one general word. where it would be called as a streaming multiprocessor. Now, what would happen? So the job would be scheduled and it would be added to this streaming multiprocessor. So the scheduler decides that which streaming processor is available and where the task should go. So there would be a cache and there would be a local memory for this particular streaming processor. Now the data has passed through, but as you can see that inside the streaming multiprocessor there are multiple instruction set which are a SIMD set, which is nothing but single instruction multiple data, and this every SIMD consists of the arithmetic logic unit for a computation. So again, each block which is a streaming multiprocessor, it has a multiple different SIMD sets and that has a multiple compute unit. So it can run within the core also far more threads parallelly. So that is what the typical GPU architecture is. So you may want to call it as, when you come to the programming, you need to assume as that there is a block which contains a capability to run multiple threads, and there is a multiple blocks when you come to the GPU designs. So there are multiple blocks with a similar behavior, and what the scheduler will be doing is that whichever the streaming multiprocessor is available, it would schedule the job. So that's a typical GPU architecture. So now that we have addressed this typical GPU architecture, now we can see that how this GPU and CPU interacts when we assume a simple program. Okay, so in the next section we will be covering that how the program would flow for a GPU program.